Welcome to Sleepless Astronomer, where we explore the wonders of space and the universe. If you're enjoying these cosmic journeys, please like this video and subscribe to the channel. We post new videos every single day, so you can tune in whenever you want to learn about the cosmos. And we'd love to hear from you in the comments. Let us know where in the world you're watching from. We always enjoy connecting with fellow space enthusiasts around the globe. Now let's begin tonight's journey through the universe. The bright and dark features on surfaces. Across the solar system, the surfaces of planets, moons, and asteroids display remarkable contrasts between light and dark regions. These variations in brightness, called albedo features, paint cosmic bodies with patterns that range from subtle shadings to stark contrasts, each telling a story about composition, geology, and the forces that have shaped these worlds over billions of years. Consider Earth's moon, the most familiar example. Even without a telescope, you can see the dramatic difference between the bright highlands and the dark Maria, the ancient lava plains that early observers mistook for seas. The bright regions are ancient crust formed over 4 billion years ago when the moon was young, and its surface was still cooling from a molten state. This primordial crust is rich in a mineral called anorthosite, a type of rock that's relatively light in colour and highly reflective. These highlands are the original surface of the moon, battered by eons of meteorite impacts, but still retaining their pale character. The dark Maria formed later, between about 3.8 and 3.1 billion years ago, when massive asteroid impacts punched through the moon's crust and allowed molten rock from the interior to flood onto the surface. This lava was basaltic, similar to the lava that flows from volcanoes in Hawaii, and it's much darker than the highland material. The basalt contains more iron and magnesium than the ancient crust, and these elements absorb more light, giving the Maria their characteristic dark appearance. When this lava cooled and solidified, it created vast, smooth plains that still dominate the near side of the moon today. The moon's far side presents a different face, with far fewer dark Maria and much more bright highland terrain. This asymmetry puzzled scientists for decades. Why would one side of the moon have so much volcanic flooding, while the other side remained mostly ancient highland? The answer lies in the moon's structure. The crust on the far side is thicker, making it harder for lava to break through, even when massive impacts occurred. The near side's thinner crust allowed molten rock to more easily reach the surface, creating the face we see each night. Mars displays its own dramatic albedo patterns, visible even through small telescopes from Earth. The planet shows bright regions and dark regions that early astronomers mapped and named, imagining them to be continents and seas. The bright areas are primarily ancient highland regions covered with fine dust that's rich in iron oxide, essentially rust, giving Mars its characteristic red colour. This dust is incredibly fine, almost like talcum powder, and it reflects sunlight fairly efficiently despite its red hue. The dark regions on Mars are areas where the dust has been blown away by winds, exposing darker underlying rock or concentrations of dark sand. Some of these features change over time as seasonal winds redistribute dust across the planet's surface. During global dust storms, which can envelope the entire planet, the contrast between bright and dark features diminishes as everything gets covered in suspended dust. As the storm settles, the patterns gradually re-emerge, though sometimes in slightly different configurations than before. One of Mars's most prominent dark features is Syrtis Major, a broad shield volcano whose dark basaltic rock stands in stark contrast to the surrounding bright highlands. This feature was one of the first to be recognized on Mars and has been used for centuries to track the planet's rotation. The dark rock here is volcanic in origin, similar to the moon's Maria, and it resists being covered by the bright dust that blankets much of the planet. Mercury, the innermost planet, shows subtle but distinct albedo variations across its heavily cratered surface. The overall planet is fairly dark, reflecting only about 12% of the sunlight that hits it, making it one of the least reflective rocky bodies in the solar system. But within this generally dark surface, brighter and darker regions exist. Some craters have bright rays extending from them, where the impact that formed the crater excavated fresher material from beneath Mercury's space-weathered surface and scattered it across the surrounding landscape. The darker regions on Mercury include vast, smooth plains that, like the Moon's maria, formed when lava flooded the surface billions of years ago. But Mercury also has mysterious dark material that appears to have been deposited from volcanic eruptions in a more explosive fashion. This dark material, which may be rich in carbon or other volatile rich compounds, creates some of the darkest features on the planet's surface, appearing almost black in high-resolution images. Jupiter's moon Europa presents one of the most striking albedo contrasts in the solar system. The moon's surface is almost entirely water ice, but it's not uniformly bright. The cleanest ice is brilliantly white, reflecting nearly all the sunlight that touches it. But cutting across this bright surface are countless dark lines and streaks, forming patterns that remind observers of cracks in pack ice on Earth. These dark features are ridges and bands where the ice has fractured and material from beneath, perhaps salts, sulfur compounds, or organic molecules, has been exposed or deposited on the surface. Some of Europa's dark features appear reddish-brown, suggesting the presence of salts like magnesium sulfate or sodium chloride that have been altered by radiation from Jupiter's intense magnetic field. The radiation breaks apart molecules and creates new compounds, darkening and discoloring the surface materials over time. The brightest regions on Europa are thought to be the youngest, places where fresh ice has recently been exposed or deposited, while the darker, more discolored regions are older surfaces that have been exposed to radiation for longer periods. Saturn's moon Iapetus displays perhaps the most dramatic albedo contrast of any body in the solar system. One hemisphere is as bright as fresh snow, reflecting about 60% of incoming sunlight, while the other hemisphere is as dark as asphalt, reflecting only about 4%. The boundary between these regions is sharp and striking, creating an appearance that reminded astronomers of a yin-yang symbol. The dark material, concentrated primarily on the leading hemisphere, the side that faces forward as Iapetus orbits Saturn, may have originated from dark dust in Saturn's system that Iapetus swept up as it moved through space, or it may have erupted from the moon's interior through cryovolcanic processes. Once the initial dark material was deposited, a feedback process likely amplified the contrast. Dark surfaces absorb more sunlight and heat up more during the day. On Iapetus, where daytime temperatures can reach as high as -230 degrees Fahrenheit in sunny areas, this slight extra heating in the dark regions causes water ice to slowly sublimate, transition directly from solid to vapor. This water vapor migrates to colder regions, including the bright trailing hemisphere, where it refreezes. Over millions of years, this process has darkened the dark hemisphere further by removing its ice and brightened the bright hemisphere by depositing additional ice there. Pluto, visited by NASA's New Horizons spacecraft in 2015, revealed a surface of surprising complexity and dramatic albedo contrasts. The dwarf planet's most prominent dark feature, informally named Cthulhu Regio, is a vast region near the equator that appears deep red-brown in colour. This dark material is thought to be complex organic molecules called tholins, formed when ultraviolet light from the distant sun and cosmic rays interact with methane and nitrogen in Pluto's thin atmosphere. These molecules rain down onto the surface, accumulating over time and creating the dark coloration. Adjacent to this dark region lies Sputnik Planitia, a vast plain of bright nitrogen ice that forms the western lobe of Pluto's heart-shaped feature. This bright ice reflects much more light than the surrounding terrain. The contrast exists because nitrogen ice is relatively bright and because this region is geologically active. The ice is constantly churning in slow convection cells, bringing fresh material to the surface and preventing the accumulation of the dark organic compounds that colour other parts of Pluto. Asteroids show their own albedo variations, though measuring them requires careful observation. Some asteroids are quite dark, reflecting only 3 or 4% of the light that hits them. These are typically carbonaceous asteroids, rich in carbon compounds and hydrated minerals, making them among the darkest natural objects known. Other asteroids are much brighter, particularly those made primarily of metal or rocky silicates. The contrast between dark and bright asteroids tells scientists about their composition and helps trace them back to different regions of the early solar system where they formed. Even within a single asteroid, albedo features can exist. Some asteroids show bright spots that might be exposed fresh material where an impact has recently broken through a darkened, space-weathered surface layer. Others show variations that might indicate different minerals or rock types at the surface. The asteroid Vesta, one of the largest in the main belt, shows dramatic brightness variations across its surface, with some regions nearly twice as reflective as others. The process called space weathering affects the brightness of surfaces throughout the solar system. When cosmic rays, solar wind particles, and micrometeorites bombard a surface over time, they gradually darken it and change its reflective properties. Fresh surfaces, recently exposed by impacts or other processes, appear brighter. Ancient surfaces that have been exposed to space for billions of years generally appear darker and redder than they would if the same material were fresh. On the Moon, this space weathering creates the subtle variations in brightness visible within both the highlands and the Maria. The rays around young craters appear bright because the impact has excavated fresh material. Over hundreds of millions of years, these rays gradually fade as space weathering darkens the ejected material, causing it to blend in with the surrounding ancient terrain. Comets show extreme albedo contrasts as well. The nucleus of a comet, the solid body beneath the gas and dust, is among the darkest objects in the solar system, often reflecting only about 4% of incident light. This dark material is thought to be a mixture of organic compounds, similar to the tholins on Pluto, mixed with dust and ice. But when a comet approaches the Sun and begins to release gas and dust, it can develop bright areas where fresh ice is exposed and actively sublimating, creating jets of gas that appear much brighter than the surrounding dark nucleus. The study of albedo features requires careful measurement. Scientists use photometry to measure exactly how much light a surface reflects at different wavelengths. By comparing the brightness at different wavelengths, they can determine not just whether a surface is bright or dark overall, but what specific materials might be present. Iron-rich minerals absorb light differently than ice, which absorbs differently than sulfur compounds or organic materials. Each substance has its own spectral signature, revealed through its albedo characteristics. These patterns of light and dark across the surfaces of solar system bodies are not mere decoration. They are maps written in brightness, showing us where different materials exist, where geologic processes have been active, where impacts have occurred, and how surfaces age under the constant bombardment of radiation and particles from space. Every bright crater ray, every dark lava plain, every reddish streak of organic material tells part of the story of how these worlds formed and evolved, creating the complex and beautiful patterns we observe across the solar system. The crystal-like structures in space, deep within the cosmos, far from the warmth of any star, materials arrange themselves into patterns that would look familiar under a microscope on Earth. These crystalline structures form in the most unexpected places, defying the assumption that space is simply a chaotic void of random particles and radiation. In the cold depths between stars, water molecules slowly drift together, each one eventually finding its place in an organized lattice. The process happens atom by atom, molecule by molecule, as temperatures hover just a few degrees above absolute zero. Unlike the rapid freezing we experience on Earth, these ice crystals have time, millions of years sometimes, to achieve near-perfect geometric arrangements. The hexagonal patterns repeat endlessly, creating structures that catch and reflect starlight in particular ways that astronomers can detect from across the galaxy. Silicate minerals also crystallize in space, forming within the cooling outflows of dying stars. As a red giant sheds its outer layers, temperatures drop from thousands of degrees to just hundreds, creating conditions where molten rock can slowly solidify into crystals. These aren't the rough, irregular chunks we might expect. They're often perfectly formed olivine crystals, the same green mineral found in beach sand on Earth, but floating freely in the vacuum between worlds. Some of these crystals are microscopic, barely larger than the wavelength of light, while others grow to sizes that would be visible to the naked eye if you could somehow hold one. The environment around young stars presents another laboratory for crystal formation. In the swirling disk of gas and dust that will eventually become planets, temperatures vary dramatically with distance from the central star. There's a boundary, a line in space, where water transitions from gas to solid ice. Scientists call this the snow line or ice line, and it's here that water crystallizes directly from vapor without ever being liquid. The crystals that form are often elaborate, with branching structures that would rival any snowflake on Earth. These become the building blocks of comets and the icy cores of giant planets. Carbon takes on crystalline forms in space as well. In the hearts of ancient stars where pressures and temperatures reach extremes, carbon atoms arrange themselves into diamond structures. These aren't the large gemstones of jewelry stores, but microscopic grains that get expelled into space when the star dies. Scientists have found these pre-solar diamonds in meteorites that have fallen to Earth, tiny time capsules that formed before our solar system even existed. Each one contains isotope ratios that don't match anything that formed near our sun, proving they crystallized around entirely different stars. The surfaces of comets hide their own crystalline secrets. When these icy bodies spend long periods in the cold outer reaches of the solar system, the water ice in them gradually transitions from an amorphous glass-like state into a crystalline form. This transition releases trapped gases, sometimes causing the comet to briefly become more active, even when it's far from the sun. The crystalline ice has a different density than the amorphous ice, creating stresses within the comet's structure that can cause chunks to break away. Methane ice crystallizes on the surfaces of distant worlds, like Pluto and Neptune's moon Triton. At the frigid temperatures found in the outer solar system, methane behaves much like water ice does on Earth. It forms mountains and plains, fills craters, and even creates frost that glitters on the surface. The crystal structure of methane ice determines how it flows and breaks, shaping these distant landscapes in ways that mirror glacial processes on Earth, but with a completely different material. Salt crystals have been detected in the geysers of Saturn's moon Enceladus. Deep beneath this tiny world's icy crust lies an ocean of liquid water, kept warm by tidal heating from Saturn's gravity. When water from this ocean erupts through cracks in the ice, it immediately begins to freeze in the vacuum of space. But before it freezes completely, dissolved salts precipitate out, forming tiny crystalline particles that get ejected into space along with the ice. These salt crystals tell scientists about the chemistry of that hidden ocean. In the dusty clouds where stars form, silicate grains develop crystalline structures that affect how they interact with light and heat. When these grains are hit by shockwaves from nearby stellar explosions, the intense but brief heating can transform their atomic structure, creating crystals with specific properties. The type of crystal that forms depends on the exact composition of the grain and the intensity of the heating event. Some become forsterite, a magnesium-rich crystal that glows warmly in infrared light. Others become enstatite, a pyroxene mineral with a different crystal lattice. The process of crystallization in space isn't always slow and gradual. Sometimes it happens in moments. When two white dwarf stars collide, the tremendous pressures and temperatures can cause carbon to crystallize almost instantaneously into diamond. The resulting object might have a core of crystallized carbon surrounded by layers of other materials, a cosmic gemstone larger than our Earth itself, hidden from view by its outer envelope. Amino acids, the building blocks of proteins, have been found in meteorites in crystalline forms. These organic crystals formed in the cold of space, where complex molecules could arrange themselves into ordered structures. The handedness of these crystals, whether they twist to the left or right, has implications for how life might have begun on Earth. The predominance of certain crystal orientations in space-formed amino acids might explain why life on Earth uses left-handed amino acids almost exclusively. Iron and nickel alloys crystallize in the cores of asteroids, forming structures called Widmanstätten patterns. These form when molten metal cools extraordinarily slowly over millions of years, allowing different crystal phases to separate and create geometric patterns. When metallic meteorites are cut, polished, and etched with acid, these patterns become visible as interlocking crystals that look almost like abstract art. The size and arrangement of these crystals tell scientists about the thermal history of the asteroid they came from. Sulfur compounds crystallize on the surface of Jupiter's moon, Io, the most volcanically active body in the solar system. The sulfur takes on different crystalline forms depending on temperature, creating a multicolored landscape of yellows, reds, oranges, and whites. Each color represents a different allotrope of sulfur, a different way the atoms can arrange themselves into crystal structures. These crystals don't last long in their original form. The intense radiation from Jupiter and the constant volcanic resurfacing mean that sulfur crystals are continually forming, breaking down, and reforming. In the coldest clouds of interstellar space, carbon dioxide freezes into dry ice crystals. These crystals coat the surfaces of dust grains, creating icy mantles that change how the grains interact with each other and with radiation. The crystal structure of this frozen carbon dioxide determines how easily it can trap other molecules, creating complex ices that contain dozens of different compounds, all organized in crystalline matrices. Phosphates and other minerals crystallize in meteorites under conditions that never occur on Earth today. These crystals preserve information about the early solar system, including the presence of water and the temperatures that existed on their parent asteroids. Some contain tiny pockets of liquid water trapped within the crystal structure, water that has been sealed away for over 4 billion years. The magnetic minerals in meteorites show evidence of crystallization in the presence of magnetic fields. The way iron oxide crystals align as they form reveals information about magnetic fields that existed around the young sun and in the interiors of molten asteroids. These crystals act as fossil compasses, recording ancient magnetic environments that have long since disappeared. Quartz crystals, so common on Earth, form in space as well, though through different processes. In the shocked material around impact sites, the intense pressure can cause silicon and oxygen to crystallize into quartz with unusual properties. Some of these crystals contain defects and inclusions that could never form under Earth's surface conditions, making them distinct markers of extraterrestrial origin. The study of crystalline structures in space reveals that the same fundamental physics that governs crystal formation in earthly laboratories operates throughout the universe. Temperature, pressure, chemical composition, and time determine what forms. but the basic rules remain constant whether the crystals form in a laboratory, deep in the Earth, or in the cold expanse between stars, where matter continues to organize itself into patterns of surprising complexity and beauty. The invisible forces holding galaxies together. When you look at a photograph of a spiral galaxy, you see a beautiful pinwheel of stars, gas, and dust rotating around a central bulge. The image suggests a structure held together by visible matter, the billions of stars whose light creates the galaxy's luminous form. But appearances are deceiving. The forces actually holding galaxies together are largely invisible, operating through mechanisms both understood and mysterious. Gravity binds these cosmic structures, but most of the mass providing that gravity cannot be seen, cannot be detected, except through its gravitational effects, and remains one of the deepest mysteries in astrophysics. The first clue that something invisible was holding galaxies together came from studying how stars move within them. In the 1970s, astronomer Vera Rubin conducted detailed observations of spiral galaxies, measuring the velocities of stars and gas clouds at various distances from the galactic centers. According to Newton's laws of motion and gravity, objects farther from the center of mass should orbit more slowly, just as Neptune orbits the Sun much more slowly than Mercury. The visible matter in galaxies is concentrated toward the center, with the brightness falling off dramatically in the outer regions. Based on this distribution of visible matter, stars in the outer parts of galaxies should be moving much slower than stars near the center. But that's not what Rubin found. Instead, the rotation curves, graphs showing orbital velocity versus distance from the center, were flat. Stars in the outer regions were moving just as fast as stars closer to the center, sometimes even faster. This could only mean one thing. There was far more mass in these galaxies than could be accounted for by visible stars, gas, and dust. This additional mass had to extend well beyond the visible disk, forming a massive spherical halo surrounding each galaxy. The nature of this dark matter remains unknown, but its gravitational effects are undeniable. Galaxies are embedded within dark matter halos that contain several times more mass than all the visible matter combined. A typical spiral galaxy, like the Milky Way, might contain about 100 billion solar masses of visible matter, stars, gas, dust, planets, but resides within a dark matter halo containing perhaps 1 trillion solar masses. This dark matter halo extends perhaps 10 times farther than the visible disk, creating a gravitational well that holds the galaxy together. Dark matter doesn't interact with light. It neither emits, absorbs, nor reflects electromagnetic radiation of any wavelength. It interacts with normal matter almost exclusively through gravity. This makes it invisible to telescopes, but reveals its presence through gravitational effects. The flat rotation curves that Rubin observed were the first clear evidence, but dark matter reveals itself in other ways as well. Gravitational lensing provides some of the most compelling evidence for dark matter in and around galaxies. According to Einstein's general theory of relativity, mass warps space-time, and light follows the curves in that warped geometry. When light from a distant galaxy passes near a massive object, its path bends. By measuring this bending and calculating how much mass would be needed to produce it, astronomers can map the distribution of mass, including dark matter. These mass maps show that dark matter is distributed in huge halos around galaxies, exactly as predicted from rotation curve studies. The bullet cluster provides particularly dramatic evidence. This structure formed when two galaxy clusters collided and passed through each other. During the collision, the hot gas from each cluster, normal matter that can interact with itself, slowed down and remained near the collision site, heated by the impact. But gravitational lensing maps show that most of the mass is not where the gas is. Instead, it separated from the gas and continued moving with the galaxies themselves. This separated mass must be dark matter, which doesn't collide or interact with normal matter except through gravity, passing right through during the cluster collision. The gravitational force from dark matter operates according to Newton's law of universal gravitation for most purposes, though general relativity provides the more accurate description, especially in strong gravitational fields. The force is proportional to the product of the masses and inversely proportional to the square of the distance between them. Even though individual dark matter particles don't clump together the way atoms do, they can't radiate energy and settle into compact structures. Collectively, they form halos through gravitational attraction, with each particle orbiting in the combined gravitational field of all the others. These dark matter halos formed before the visible galaxies themselves. In the early universe, dark matter could begin collapsing into clumps earlier than normal matter, because dark matter doesn't interact with radiation. Normal matter, coupled to photons in the early universe, couldn't collapse efficiently until after recombination, when electrons combined with nuclei to form neutral atoms, and the universe became transparent. By that time, dark matter had already created gravitational wells, regions of enhanced density, and normal matter fell into these wells, forming the first galaxies within the scaffolding of dark matter structure. Computer simulations of galaxy formation must include dark matter to reproduce the observed properties of galaxies. Simulations using only normal matter produce galaxies that look nothing like what we observe. But when dark matter is included, with properties consistent with observations, non-interacting except through gravity, with a specific abundance relative to normal matter, the simulations produce galaxies remarkably similar to real ones, with flat rotation curves, realistic sizes, and appropriate clustering properties. The dark matter distribution within galaxies follows a characteristic profile. The density is highest at the center and decreases toward the outer regions, but much more gradually than the distribution of visible matter. Various mathematical models describe this distribution, with names like the NFW profile, named after Julio Navarro, Carlos Frenk, and Simon White, who studied dark matter halos in simulations in the 1990s. These profiles predict specific density distributions that can be tested against observations through rotation curves and gravitational lensing. But dark matter isn't the only force holding galaxies together. Gravity from visible matter contributes as well, though less than dark matter. The combined gravitational pull from billions of stars, gas clouds, dust, and the supermassive black hole at the center all help bind the galaxy. The distribution of this visible matter creates the gravitational potential in which stars orbit, and while dark matter dominates the total mass, the visible matter shapes the inner regions where most stars reside. Orbital mechanics plays a crucial role in keeping galaxies stable. Each star orbits in the combined gravitational field of all other matter in the galaxy, both visible and dark. Stars don't simply circle the galactic center in perfect circles like planets orbiting the Sun. Their orbits are more complex, elliptical, and tilted at various angles, creating the three-dimensional structure of the galaxy. In spiral galaxies, the disk forms because stars that were born from a rotating cloud of gas inherited that rotation, and collisions between gas particles dissipated energy and flattened the distribution into a disk. The supermassive black hole at the center of most galaxies contributes to holding the inner regions together, though its mass is typically small compared to the total galaxy mass, perhaps 0.1 to 1% of the bulge mass. The black hole at the center of the Milky Way, Sagittarius A star, contains about 4 million solar masses. While this is enormous by any terrestrial standard, it's tiny compared to the Milky Way's total mass of perhaps 1 trillion solar masses, including dark matter. The black hole's gravitational influence dominates only in the innermost few light years, Spiral density waves also play a role in galactic structure, though they're not forces holding the galaxy together in the same sense as gravity. These waves are regions of enhanced density that rotate through the disk, compressing gas and triggering star formation. The spiral arms we see are not fixed structures, with the same stars always in them, but rather patterns that rotate at a different speed than the stars themselves. Stars move in and out of the spiral arms as they orbit, spending more time in the arms where the density is higher, creating the appearance of persistent spiral structure. Galaxy clusters add another layer of complexity. Galaxies themselves are held together primarily by their dark matter halos, but galaxies cluster together in groups and clusters, which are themselves held together by even larger dark matter halos. The Milky Way is part of the local group, which includes the Andromeda Galaxy and about 50 smaller galaxies, all orbiting within a common dark matter halo. Galaxy clusters, like the Virgo cluster, contain thousands of galaxies within a massive dark matter halo containing quadrillions of solar masses. The dynamical state of galaxies, whether they're stable, expanding, or contracting, depends on the balance between kinetic and potential energy. If the kinetic energy of all the stars and gas exceeds twice the magnitude of the gravitational potential energy, the galaxy would be unbound and would eventually fly apart. The fact that galaxies remain bound over billions of years tells us that they're in virial equilibrium, a state where kinetic and potential energy are balanced according to the virial theorem. This relationship allows astronomers to estimate the total mass of galaxies from observations of how fast their contents are moving. Some alternative theories propose that dark matter doesn't exist, and that instead, our understanding of gravity needs modification. Modified Newtonian dynamics, or MOND, proposed by Mordechai Milgram in 1983, suggests that gravity behaves differently at very low accelerations, like those experienced by stars in the outer regions of galaxies. MOND can reproduce flat rotation curves without dark matter, but it struggles to explain other observations like gravitational lensing and the bullet cluster. Most physicists consider dark matter more likely to be a new type of particle rather than a modification of gravity, though the question remains open until dark matter is directly detected or conclusively ruled out. The search for dark matter particles continues in laboratories around the world. Experiments deep underground attempt to detect rare interactions between dark matter particles and normal matter. Other experiments search for signals of dark matter particles annihilating with each other or decaying into detectable particles. The Large Hadron Collider attempts to create dark matter particles in high-energy collisions. So far, no experiment has definitively detected dark matter particles, but each null result constrains the possible properties of dark matter, narrowing the possibilities. The invisible forces holding galaxies together operate on timescales of hundreds of millions to billions of years. A star near the Sun's position in the Milky Way takes about 225 million years to complete one orbit around the galactic center. During this time, the combined gravitational pull from the dark matter halo, the visible matter in the disk and bulge, and all other components keeps the star bound to the galaxy. The stability of this configuration over billions of years, galaxies don't fly apart, they maintain their structures over cosmic time, testifies to the power and precision of the gravitational forces at work. Understanding the invisible forces holding galaxies together remains one of the central challenges in astrophysics. The existence of dark matter is now accepted by most scientists based on the overwhelming gravitational evidence, but its fundamental nature remains mysterious. Whether it consists of weakly interacting massive particles, axions, primordial black holes, or something entirely unexpected, dark matter's gravitational pull provides the invisible glue that holds galaxies together. shapes their structure, determines their evolution, and creates the cosmic web of large-scale structure that defines the universe on the largest scales, making dark matter's invisibility one of the most tantalizing mysteries in science, a substance that makes up most of the universe's mass, but reveals itself only through the ancient and universal force of gravity that governs the motion of everything, from falling apples to orbiting galaxies. The solar wind that flows through space. From the surface of the sun, an invisible river flows outward in all directions, streaming past the planets and extending far beyond the orbit of Pluto into the distant reaches of the solar system. This is the solar wind, a continuous flow of charged particles, primarily electrons and protons, that escape from the sun's outer atmosphere and race through space at speeds ranging from 250 to over 500 miles per second. This wind carries with it pieces of the sun itself, along with magnetic fields that thread through the solar system, creating an enormous bubble of solar influence that shapes the space environment around every planet. The story of the solar wind begins in the sun's corona, the outermost layer of the solar atmosphere that extends millions of miles above the visible surface. The corona is paradoxically much hotter than the surface below it, while the sun's visible surface, the photosphere, has a temperature of about 10,000 degrees Fahrenheit. The corona reaches temperatures exceeding 2 million degrees. This extreme heating, still not completely understood, but likely involving magnetic fields and wave energy, gives particles in the corona so much energy that many of them move faster than the sun's escape velocity. Imagine standing at the sun's surface and throwing a baseball upward. To escape the sun's gravity, you would need to throw it at about 380 miles per second. In the corona, thermal energy heats particles to such extreme temperatures that a significant fraction of them are moving faster than this escape velocity. These particles don't fall back to the sun. They stream away into space, carrying energy and momentum with them. The sun is essentially evaporating, losing mass continuously through this process, though at a rate so slow that it would take trillions of years to evaporate completely. The solar wind is not uniform. It flows faster from some regions of the sun than others, creating a complex structure as it expands outward. Above the sun's equatorial regions, where magnetic field lines tend to loop back to the surface, the solar wind emerges more slowly, typically around 250 miles per second. But at the sun's poles and in coronal holes, regions where magnetic field lines extend far into space, rather than looping back, the wind flows much faster, reaching speeds of 500 miles per second or more. These variations in speed create interaction regions where fast solar wind catches up to slow solar wind. Imagine cars on a highway where fast-moving traffic overtakes slower-moving traffic. The fast solar wind compresses the slow solar wind ahead of it, creating regions of enhanced density and magnetic field strength. These co-rotating interaction regions, named because they rotate with the sun as it spins, sweep through the solar system like a spiral pattern, buffeting planets with alternating streams of slow and fast wind. As the solar wind flows outward, it carries the sun's magnetic field with it. The magnetic field lines become stretched and twisted, creating a spiral pattern much like water from a rotating garden sprinkler. This interplanetary magnetic field threads through the entire solar system, connecting magnetically active regions on the sun to the distant reaches of space. When magnetic field lines from different regions of the sun come together, in space they can reconnect, releasing energy and accelerating particles to even higher speeds. The solar wind is not just a steady breeze but includes violent gusts and storms. When an eruption occurs on the sun, a solar flare or a coronal mass ejection, enormous quantities of plasma and magnetic field can be hurled into space far faster than the normal solar wind. A coronal mass ejection can contain billions of tons of material moving at speeds up to several thousand miles per second. When one of these structures reaches Earth, typically 1 to 3 days after leaving the Sun, it can compress Earth's magnetic field, trigger spectacular auroras, and potentially disrupt satellites, power grids, and communication systems. The journey of a solar wind particle from the Sun to Earth takes about 4 to 5 days travelling at typical speeds. During this journey, the particle encounters very little. Space between the Sun and Earth is remarkably empty. A cubic inch of the solar wind near Earth contains only about 5 to 10 protons, far more tenuous than even the best vacuum we can create in laboratories on Earth. Yet despite this extreme sparseness, the solar wind carries significant momentum and energy simply because of the vast volume through which it flows and the speeds at which it travels. When the solar wind encounters a planet, what happens depends on whether that planet has a magnetic field. Earth's magnetic field creates a protective bubble called the magnetosphere that deflects most of the solar wind around the planet. The interaction is dynamic and complex. The leading edge of Earth's magnetosphere, called the bow shock, is where the supersonic solar wind first encounters Earth's magnetic field and slows down abruptly, much like air piling up in front of a supersonic aircraft creates a shock wave. This shock heats the solar wind and diverts it around Earth's magnetosphere, creating a turbulent boundary layer called the magnetosheath. Some solar wind particles do manage to penetrate into Earth's magnetosphere, particularly when reconnection occurs between the interplanetary magnetic field and Earth's magnetic field. These particles get funneled along Earth's magnetic field lines toward the polar regions, where they collide with atoms in the upper atmosphere, creating the shimmering curtains of light we call auroras. The green and red colours come from oxygen atoms at different altitudes being excited by these collisions, while nitrogen produces blue and purple hues. Planets without magnetic fields like Mars and Venus experience the solar wind very differently. Without a protective magnetic bubble, the solar wind interacts directly with the upper atmosphere. Over millions of years, this interaction strips away atmospheric particles, carrying them off into space. Mars, which once had a thicker atmosphere and possibly liquid water on its surface, has lost much of its atmosphere to this process. The solar wind literally peels away the outer layers of the Martian atmosphere, particularly during strong solar storms, gradually transforming Mars from a potentially habitable world to the thin, dry atmosphere we observe today. The Moon, with neither atmosphere nor magnetic field, receives the full force of the solar wind directly on its surface. Solar wind particles impact the lunar regolith, becoming implanted in the soil. Over billions of years, this process has altered the chemistry and appearance of the lunar surface, darkening it and creating what scientists call space weathering. Ancient lunar rocks brought back by Apollo astronauts contain trapped solar wind particles that serve as a record of how the Sun's output has changed over time. Giant planets like Jupiter and Saturn have enormous magnetospheres that extend millions of miles into space. Jupiter's magnetosphere is so large that if we could see it from Earth, it would appear several times larger than the full moon in the sky. The solar wind compresses these magnetospheres on the side facing the Sun and stretches them into long tails on the night side. Within these giant magnetospheres, the interaction between the solar wind, the planet's magnetic field, and particles from the planet's moons creates some of the most intense radiation environments in the solar system. The solar wind doesn't flow forever. Far from the Sun, billions of miles beyond the orbits of the planets, it begins to slow down as it encounters the interstellar medium, the dilute gas and plasma that fills the space between stars. The Voyager spacecraft, launched in 1977, have travelled far enough to cross the boundary where the solar wind slows to subsonic speeds, called the termination shock. This boundary is not spherical, but is pushed outward in the direction the solar system is moving through the galaxy and compressed in the opposite direction. Beyond the termination shock lies a region called the heliosheath, where the solar wind has slowed but still moves outward, compressed and heated by its interaction with the interstellar medium. The exact shape and extent of this region depend on the strength of the solar wind and the pressure of the interstellar medium outside. Voyager 1 and Voyager 2 have now crossed even farther, passing through the heliopause, the outer boundary where the solar wind effectively stops and interstellar space begins. They are now in a region where the dominant flow is no longer from the Sun, but from the galaxy itself. The structure created by the solar wind, this vast bubble of solar influence, extending billions of miles in all directions, is called the heliosphere. It serves as a partial shield, deflecting some of the cosmic rays that stream through the galaxy. Without this protection, the flux of high-energy particles reaching the inner solar system would be higher, potentially affecting planetary atmospheres and creating more radiation hazards for any life on planetary surfaces. The solar wind varies with the Sun's activity cycle. During solar maximum, when the Sun is most active with many sunspots and frequent eruptions, the solar wind is stronger, more variable, and more likely to include fast-moving coronal mass ejections. During solar minimum, when the Sun is quieter, the wind becomes more regular, though still continuous. This 11-year cycle affects space weather throughout the solar system, influencing everything from auroral activity on Earth to the radiation environment encountered by spacecraft. The composition of the solar wind provides a sample of the Sun's outer layers. While predominantly hydrogen, both protons and electrons, the wind also contains helium, making up about 4% of the particles, along with trace amounts of heavier elements, like carbon, nitrogen, oxygen, neon, magnesium, silicon, and iron. These heavier elements are present in much smaller quantities but provide valuable information about solar composition and the processes occurring in the corona. Different types of solar wind have different characteristics. The slow solar wind is denser and cooler, while the fast wind is more tenuous but carries more kinetic energy due to its higher speed. Transient events like coronal mass ejections create temporary structures in the solar wind with dramatically enhanced density, speed, and magnetic field strength. These variations create a constantly changing space environment that spacecraft and planets must navigate. The solar wind also carries information outward from the Sun. Disturbances created by solar activity propagate through the solar wind, and by observing how these disturbances evolve and interact as they move through space, scientists can learn about the properties of the wind itself and the magnetic fields threading through it. Spacecraft throughout the solar system serve as sentinels, measuring the solar wind's properties at different locations and providing a three-dimensional view of how this invisible river flows through our cosmic neighborhood. Every star produces a stellar wind, analogous to our solar wind, and these winds play important roles in stellar evolution and in shaping the environments around other planetary systems. Hot, massive stars produce fierce stellar winds that can carry away significant fractions of the star's mass over its lifetime. Cool, evolved stars like red giants produce slower but denser winds. Understanding our own solar wind provides insights into these stellar winds throughout the galaxy, connecting the processes occurring in our immediate space environment to the broader evolution of stars and planetary systems across the universe. The thick atmospheres of Jupiter and Saturn. Jupiter and Saturn are fundamentally different from the rocky planets of the inner solar system. They have no solid surface to stand on, no ground beneath the sky. Instead, these gas giants are essentially enormous atmospheres all the way down, layers upon layers of gas that gradually transition from thin upper hazes to dense, crushing depths, where pressure transforms hydrogen into states of matter that don't exist naturally anywhere on Earth. Understanding these thick atmospheres means understanding worlds where the atmosphere isn't just a thin shell surrounding a planet, it is the planet. The atmospheres of Jupiter and Saturn are composed primarily of hydrogen and helium, the two lightest and most abundant elements in the universe. Jupiter's atmosphere is about 90% hydrogen and 10% helium by number of molecules, with trace amounts of methane, ammonia, water vapor, and other compounds making up less than 1%. Saturn has a similar composition, though with slightly less helium, about 96% hydrogen and 3% helium, with the missing helium thought to have settled deeper into the planet's interior over billions of years. This composition mirrors the composition of the Sun and the primordial solar nebula from which the planets formed, marking these giants as worlds that captured and retained their original atmospheres from the planet-forming disk. The visible clouds we see when we look at Jupiter and Saturn exist in the uppermost layers of these atmospheres, in a region where temperatures and pressures allow various compounds to condense into droplets and crystals. On Jupiter, the highest cloud layer consists of ammonia ice crystals forming at temperatures around -150 degrees Celsius, where ammonia gas freezes into white ice. These ammonia clouds give Jupiter's zones, the bright bands that circle the planet, their brilliant white appearance. Below this ammonia layer, at slightly higher temperatures and pressures, ammonium hydrosulfide forms another cloud deck, creating brown and tan colours. Deeper still, water ice and liquid water droplets form clouds, though these are rarely visible from above, hidden beneath the overlying layers. Saturn's cloud structure is similar but more subdued. The planet appears more uniformly golden tan because a high-altitude haze of unknown composition partially obscures the underlying cloud layers. This haze may consist of complex organic molecules called tholins, created when ultraviolet light from the Sun breaks apart methane molecules in the upper atmosphere, allowing the fragments to recombine into larger, more complex hydrocarbons. These organic hazes absorb blue light and scatter red and yellow light, giving Saturn its characteristic buttery colour. The temperatures in these atmospheres change dramatically with depth. At the cloud tops, where pressure is similar to Earth's atmospheric pressure at sea level, temperatures on Jupiter hover around -145 degrees Celsius. On Saturn, they're even colder, around -180 degrees Celsius, because Saturn is nearly twice as far from the Sun and receives less solar heating. But as you descend into these atmospheres, temperatures rise rapidly. The increase comes partly from the Sun's heat that has been absorbed and transported downward, but more significantly from the planet's internal heat. Both Jupiter and Saturn emit more energy than they receive from the Sun. Jupiter radiates about 1.7 times as much energy as it absorbs from sunlight, while Saturn radiates about 1.8 times as much. This extra energy comes from the planet's interiors. Jupiter is still slowly contracting under its own gravity, a process that converts gravitational potential energy into heat through a mechanism called Kelvin-Helmholtz contraction, named after the physicists Lord Kelvin and Hermann von Helmholtz, who described this process in the 19th century. Saturn has an additional heat source. Helium is slowly separating from hydrogen in its interior and sinking toward the center, releasing gravitational energy as it falls. Much like rain falling through Earth's atmosphere releases energy. This internal heat drives powerful convection in the atmospheres. Warm gas rises from the depths, cools as it rises and expands, then sinks back down to be heated again. This convection creates enormous circulation cells that organize the atmospheres into the distinctive banded patterns visible on both planets. Rising gas forms the bright zones, where fresh ammonia ice crystals condense and create white clouds. Sinking gas forms the darker belts, where descending motion prevents cloud formation and allows us to see deeper into the atmosphere, where darker compounds and higher temperatures exist. The winds on Jupiter and Saturn are among the strongest in the solar system. Jupiter's equatorial region rotates faster than the rest of the planet, with winds reaching speeds of about 360 kilometers per hour, roughly 225 miles per hour. Saturn's equatorial winds are even more extreme, racing along at up to 1,800 kilometers per hour, over 1,100 miles per hour, making them the fastest planetary winds in the solar system. These winds are organized into jet streams, narrow bands of fast-flowing gas that separate the zones and belts. The jet streams are remarkably stable, maintaining their positions and speeds for decades or longer. The Great Red Spot on Jupiter is perhaps the most famous atmospheric feature in the solar system. This enormous storm, large enough to swallow 2 or 3 Earths, has been observed continuously since at least 1830, and possibly as far back as the 1660s, when early telescope observers noted a large spot on Jupiter. The storm is an anticyclone, rotating counterclockwise in Jupiter's southern hemisphere, with winds at its edges reaching 400 kilometers per hour. The storm's longevity remains somewhat mysterious. On Earth, hurricanes dissipate within days or weeks when they move over land or cooler water, but the Great Red Spot has persisted for centuries. Its stability likely comes from the fact that Jupiter has no solid surface to create friction and slow the winds, and the storm may draw energy from the smaller storms it absorbs, and from the temperature difference between the warm interior and cold upper atmosphere. Saturn hosts similar, but generally smaller and shorter-lived storms. Approximately once per Saturnian year, about every 30 Earth years, a massive storm erupts in Saturn's northern hemisphere, growing to encircle the entire planet before eventually dissipating. These great white spots, as they're called, were observed in 1876, 1903, 1933, 1960, 1990, and 2010, following a remarkably regular pattern tied to Saturn's seasons. The storms appear to originate when seasonal heating destabilizes the atmosphere, allowing deep, moist convection to punch through the stable layers above and create violent thunderstorms. Lightning occurs on both Jupiter and Saturn, detected by the Voyager, Galileo, and Cassini spacecraft through radio emissions, and in some cases visible flashes. The lightning on these worlds is similar to terrestrial lightning, electrical discharges between regions of different charge within clouds, but can be far more powerful than Earth's lightning. Individual lightning bolts on Saturn have been measured at up to 1 million times more powerful than typical lightning on Earth. These storms occur in the water cloud layer, where the same process that creates thunderstorms on Earth, rising moist air forming clouds and separating electrical charges, operates on these giant planets. As you descend deeper into these atmospheres, the pressure increases relentlessly. At depths of a few hundred kilometers below the cloud tops, pressures reach thousands of times Earth's atmospheric pressure, and temperatures climb to hundreds of degrees Celsius. The atmosphere becomes denser and denser, transitioning gradually from gas to liquid, though there's no sharp boundary, no ocean surface where you suddenly plunge from air into water. Instead, the hydrogen and helium gradually become so compressed that they take on liquid properties, while still being hot enough that calling them liquid doesn't quite capture their state. They exist in a supercritical fluid state, where the distinction between gas and liquid breaks down. Descend even deeper, to depths of 10,000 to 20,000 kilometers, and pressures reach millions of times Earth's atmospheric pressure. Under these extreme conditions, hydrogen transforms into metallic hydrogen, a state of matter where the atoms are squeezed so tightly that their electrons are freed from individual atoms and flow through the material like electrons in a metal. This metallic hydrogen is thought to make up the bulk of Jupiter's mass and a significant portion of Saturn's. It's an excellent electrical conductor, and the flow of metallic hydrogen in these regions, driven by the planet's rotation and internal convection, generates the powerful magnetic fields that both planets possess. The transition from molecular hydrogen to metallic hydrogen isn't abrupt. there's a gradual change over a range of depths where hydrogen takes on increasingly metallic properties. Scientists study this transition using laboratory experiments that compress hydrogen to extreme pressures and sophisticated computer simulations that model how atoms behave under conditions impossible to fully recreate on Earth. Understanding metallic hydrogen is crucial for understanding the interiors of Jupiter and Saturn, yet its properties remain uncertain because the pressures required, several million times atmospheric pressure, can only be achieved briefly in laboratory settings. At the very centers of Jupiter and Saturn may lie rocky cores, though whether these cores exist and how large they might be remains debated. Jupiter might have a core of rock and ice containing 10 to 20 Earth masses, or it might have no distinct core at all, just a gradual increase in the concentration of heavy elements toward the center. Saturn might have a similar core, though perhaps smaller relative to the planet's total mass. NASA's Juno mission to Jupiter and the Cassini mission's final orbits, diving between Saturn and its rings, have provided gravity measurements precise enough to constrain the planet's interior structures, revealing that both planets have somewhat diffuse cores rather than sharp boundaries between core and envelope. The scale of these atmospheres is almost incomprehensible. On Earth, the atmosphere extends perhaps 100 kilometers before space begins. On Jupiter and Saturn, the atmosphere extends downward for thousands upon thousands of kilometers, transitioning through states from thin gas to dense supercritical fluid to liquid metallic hydrogen. If you could somehow survive the crushing pressures and searing temperatures and descend through Jupiter's atmosphere, it would take days or weeks of continuous falling to reach the planet's center, passing through layer after layer of hydrogen in different states, all of it technically atmosphere, because there's no solid surface to mark where the atmosphere ends. The study of Jupiter's and Saturn's atmospheres extends beyond academic interest. Understanding how these atmospheres work, how convection organizes into bands, how storms form and persist, how energy is transported from the interior to space, helps scientists understand atmospheric dynamics more broadly. The principles governing Jupiter's atmosphere apply, with appropriate modifications, to Saturn's atmosphere, to the atmospheres of Uranus and Neptune, and even to the atmospheres of giant exoplanets orbiting other stars. Some exoplanets, called hot Jupiters, orbit extremely close to their stars and have atmospheres heated to thousands of degrees, creating extreme versions of the processes we observe on Jupiter and Saturn. These thick atmospheres also serve as laboratories for studying hydrogen under extreme conditions. Most of the normal matter in the universe is hydrogen, and understanding how it behaves under high pressure is crucial for understanding not just giant planets, but also brown dwarfs, objects intermediate in mass between planets and stars, and the interiors of low-mass stars. The hydrogen in Jupiter and Saturn exists across a range of pressures and temperatures that spans from Earth-like conditions in the upper atmosphere to conditions approaching those in stellar interiors in the metallic hydrogen regions, providing natural experiments that inform our understanding of matter itself across a vast range of conditions. The incredible density of neutron stars. Imagine taking the entire mass of our Sun, a sphere so large that over 1 million Earths could fit inside it, and compressing it down to the size of a city. Not a large metropolitan area, sprawling across thousands of square miles, but just the central core, perhaps 12 or 15 miles across. This is a neutron star, an object so dense that a single teaspoonful of its material would weigh about 1 billion tons on Earth. To put that in perspective, that single teaspoon would weigh more than all the cars, trucks and buildings in a major city combined. This density is so extreme that it represents a fundamentally different state of matter, one that can only exist under the most extraordinary conditions in the universe. Neutron stars are born in the violent death throes of massive stars. When a star much larger than our Sun, typically at least 8 times more massive, exhausts the nuclear fuel in its core, it can no longer generate the heat and pressure needed to support itself against its own gravity. The core collapses catastrophically in less than a second, falling inward at speeds approaching a quarter of the speed of light. The outer layers of the star, rebounding from this collapse, are blown away in a supernova explosion that briefly outshines an entire galaxy. What remains at the center, crushed under its own gravity to densities that boggle the mind, is a neutron star. To understand how neutron stars achieve such incredible density, you need to understand what happens to matter under extreme compression. In normal matter, atoms are mostly empty space. The nucleus of an atom containing protons and neutrons occupies only a tiny fraction of the atom's volume. The rest is empty space with a few electrons orbiting at relatively vast distances. In a solid object, like a piece of iron or a rock, the atoms are packed as closely together as the electromagnetic forces between them allow. But there's still enormous amounts of empty space within each atom. As you compress matter to higher and higher densities, you eventually overcome the forces that keep atoms intact. The electrons are stripped away from their nuclei, creating a plasma of free electrons and atomic nuclei. Compress further, and the electrons themselves are forced to occupy higher and higher energy states due to quantum mechanical principles. Eventually, at densities found in white dwarf stars, electron degeneracy pressure provides the support against gravity. The electrons can't be compressed any further without violating the Pauli exclusion principle, which forbids identical particles from occupying the same quantum state. But if you compress matter beyond even this point, as happens in the core collapse of a massive star, something remarkable occurs. The electrons are forced so close to the protons in atomic nuclei that they combine through a process called electron capture. A proton and an electron merge to form a neutron, releasing a neutrino in the process. This happens not just occasionally, but to nearly every proton in the collapsing core. Within a fraction of a second, the matter that was once composed of atoms, with protons, neutrons, and electrons maintaining their separate identities, transforms into a sea of neutrons, packed together so tightly that they're essentially touching. The neutrons themselves now provide the pressure that supports the star against further collapse. Just like electrons, neutrons obey the Pauli exclusion principle and cannot be compressed indefinitely. This neutron degeneracy pressure halts the collapse, but only after the matter has been compressed to densities comparable to that of an atomic nucleus. In fact, you can think of a neutron star as essentially a single gigantic atomic nucleus, several kilometers across, containing more neutrons than there are atoms in all the planets of our solar system combined. The density at the center of a neutron star is estimated to be around 500 million to perhaps a billion tons per cubic centimeter. At these densities, a cubic centimeter, about the size of a sugar cube, would contain more mass than Mount Everest. The entire mass of humanity, every person on Earth, could be compressed into a volume smaller than a grain of sand at neutron star densities. These numbers are so far beyond everyday experience that they almost lose meaning, but they represent real physical conditions that exist in these objects. The structure of a neutron star is complex and layered. At the surface, there's a thin atmosphere only a few centimeters thick, composed of hydrogen, helium, or heavier elements, depending on the star's history. Below this lies the outer crust, where matter exists in a crystalline lattice. Here, atomic nuclei, now incredibly neutron-rich and unlike any nuclei found on Earth, are arranged in a solid structure with a sea of electrons moving between them. This crust is extraordinarily rigid. It's been calculated that the material of a neutron star's crust is about 10 billion times stronger than steel. Deeper into the neutron star, at densities about 1 million times that of normal atomic nuclei, the inner crust begins. Here, neutrons start to leak out of the nuclei and form a superfluid that exists between and around the nuclei. A superfluid is a state of matter with zero viscosity. It flows without any resistance whatsoever. This neutron superfluid can exhibit bizarre quantum mechanical behavior on a macroscopic scale. Below the crust lies the outer core, where the density becomes so high that nuclei dissolve entirely into a uniform liquid of neutrons, with a small admixture of protons and electrons to maintain charge neutrality. The neutrons in this region form a superfluid, while the protons form a superconductor, a state where electrical current can flow without resistance. These quantum fluids make up the bulk of the neutron star's interior. At the very center, in the inner core, conditions become so extreme that we're not entirely certain what happens. The density may exceed that of atomic nuclei by a factor of several times. At these densities, neutrons themselves might break down into their constituent quarks, creating what's called a quark-gluon plasma or strange quark matter. Alternatively, other exotic particles predicted by physics but never observed might appear. The center of a neutron star is one of the few places in the universe where matter exists in states that can't be recreated or studied in laboratories on Earth. The incredible density of neutron stars creates gravitational fields so strong that they noticeably warp space-time. At the surface of a neutron star, gravity is about 200 billion times stronger than on Earth. If you could somehow stand on a neutron star's surface, though you would instantly be crushed and vaporized, you would weigh 200 billion times more than you do on Earth. A fall from even a tiny height of 1 centimeter would be fatal, as you would hit the surface at a significant fraction of the speed of light. This intense gravity affects light itself. Photons climbing out of a neutron star's gravitational well lose energy through gravitational redshift. Light that starts as high-energy X-rays at the surface might emerge as lower-energy radiation by the time it escapes into space. The gravity also bends light rays, causing light from the far side of the neutron star to curve around and become visible to an observer. This means you could potentially see more than half of the neutron star's surface at once, as light from behind the star bends around it to reach your eyes. The intense gravity also means that space and time are severely warped near a neutron star. Clocks at the surface of a neutron star run about 30% slower than clocks far away in flat space-time. This time dilation is a real physical effect. Processes genuinely occur more slowly in the strong gravitational field at the surface compared to regions far from the star. The rotation of neutron stars adds another layer of extremes to their already extreme nature. Many neutron stars spin rapidly, some completing hundreds of rotations per second. This happens because of conservation of angular momentum. When the core of the parent star collapses, any rotation it had is amplified enormously as the radius shrinks. Just as a figure skater spins faster when pulling their arms in, a collapsing stellar core spins faster as it shrinks. The result can be a neutron star spinning so fast that its equator is moving at a significant fraction of the speed of light. The fastest spinning neutron star known rotates 716 times per second. Imagine an object with more mass than the Sun, compressed to the size of a city, spinning around more than 700 times every second. The surface at the equator of this neutron star is moving at about 24% of the speed of light. At these rotation rates, centrifugal forces become significant, causing the neutron star to bulge at the equator and flatten at the poles. Yet even with this rapid rotation and the outward force it creates, the neutron star holds together, a testament to the incredible strength of neutron degenerate matter and the overwhelming power of its gravity. The magnetic fields of neutron stars are among the strongest in the universe. The collapse that forms a neutron star compresses and amplifies any magnetic field present in the parent star's core. The result can be magnetic fields 1 trillion times stronger than Earth's magnetic field. Some neutron stars, called magnetars, have fields even stronger, up to 1,000 times more intense still. At these field strengths, quantum mechanical effects become important. The vacuum of space itself becomes polarized by the magnetic field, affecting how light propagates. Atoms stretched by these fields become elongated, many times longer than they are wide, fundamentally changing their properties. These magnetic fields, combined with rapid rotation, power some of the most energetic phenomena in the universe. Charged particles, accelerated along magnetic field lines, emit beams of radiation from the magnetic poles. If these beams sweep across Earth as the neutron star rotates, we detect regular pulses of radiation, which is why many neutron stars are called pulsars. The precision of these pulses rivals that of atomic clocks, with some pulsars maintaining their timing to within microseconds over years or decades. The density of neutron stars also means that they have very deep gravitational wells. The escape velocity from the surface of a typical neutron star is about 150,000 kilometers per second, roughly half the speed of light. This means that matter falling onto a neutron star from a companion star in a binary system releases tremendous amounts of energy. The infalling material accelerates to these extreme velocities and slams into the surface with incredible force, heating to temperatures of hundreds of millions of degrees and emitting intense X-rays and gamma rays. Neutron stars can also collide with each other in binary systems where two neutron stars spiral together due to the emission of gravitational waves. When they finally merge, the collision creates conditions even more extreme than those in individual neutron stars. The merger produces a burst of gravitational waves that ripple through space-time, along with electromagnetic radiation across the spectrum. These collisions are thought to be the primary source of heavy elements like gold and platinum in the universe, forged in the incredibly dense, hot material ejected during the merger. The study of neutron stars provides a unique laboratory for physics under extreme conditions. The densities, magnetic fields, rotation rates, and gravitational fields found in and around neutron stars simply don't exist anywhere else that we can observe. By studying these objects, physicists can test theories about how matter behaves at nuclear densities, how gravity warps spacetime in strong field regimes, and how quantum mechanics manifests on macroscopic scales. Every observation of a neutron star, every measurement of its mass, radius, rotation, or cooling rate provides constraints on fundamental physics that cannot be obtained any other way, offering glimpses into realms of matter and energy that push the very boundaries of our understanding. The different types of habitable planets. When astronomers speak of habitable planets, they often mean worlds similar to Earth, rocky planets with liquid water on their surfaces, orbiting at comfortable distances from sun-like stars. But the discovery of thousands of exoplanets over the past few decades has revealed that planetary systems come in astonishing variety, with planet types that don't exist in our solar system and orbital configurations that defy early expectations. This diversity suggests that habitability, the capacity to support life, might extend far beyond Earth-like worlds to encompass planet types that seem alien at first glance, yet might provide suitable conditions for life to emerge and thrive. Understanding the different types of habitable planets means expanding our definition of habitability beyond the familiar, to consider the full range of worlds where biology might find a foothold. Ocean worlds represent perhaps the most common type of potentially habitable planet. These are planets covered entirely or nearly entirely by deep oceans, with no dry land or only minimal landmass protruding above water. Earth itself is an ocean world to some degree, with about 70% of its surface covered by water, but true ocean worlds might have water covering 95 or even 100% of the surface, with global oceans potentially hundreds of kilometers deep. Such worlds might form beyond the snowline in their stellar systems, where water ice is abundant during formation, then migrate inward to warmer regions where the ice melts, creating global oceans. Life on ocean worlds might never develop terrestrial forms. Everything would evolve in water, from microscopic plankton to potentially large swimming organisms analogous to whales. Without land, there would be no forests, no land animals, no terrestrial plants. But aquatic life could still be extraordinarily diverse and complex. The key question for ocean worlds is whether photosynthetic life could evolve. Sunlight penetrates only the upper layers of water, so photosynthesis would be restricted to the surface zone. Below a certain depth, life would depend on organic matter sinking from above, or on chemical energy from hydrothermal vents on the ocean floor, much like deep-sea ecosystems on Earth. Extremely deep oceans present another challenge: high-pressure ice. At depths exceeding several hundred kilometers, pressure can become so intense that water freezes despite high temperatures, forming exotic ice structures called Ice 6, Ice 7, and other high-pressure phases that are denser than liquid water. A planet with oceans deep enough to reach these pressures would have a layer of exotic ice separating the liquid ocean from the rocky mantle below. This ice layer would prevent direct contact between water and rock, potentially limiting the availability of minerals and nutrients dissolved from rock that life might need. However, the ice itself might crack due to tidal forces or internal heat, allowing some exchange between the rocky interior and the ocean. Desert planets represent the opposite extreme, worlds where water is scarce, with most of the surface covered by deserts, sand dunes, or bare rock. These planets orbit closer to the inner edge of the habitable zone, where temperatures are higher and water is more likely to evaporate. Any water present might be concentrated in polar ice caps, in subsurface aquifers, or in rare oases where geological features trap moisture. Mars represents a partial example, a cold desert world where water exists mostly as ice or locked in minerals, with liquid water appearing only occasionally in specific locations. Life on desert planets would need extreme water conservation strategies. Organisms might be active only during rare rain events, spending most of their time dormant. They might extract water from humidity in the air or from chemical reactions rather than drinking liquid water. They might have impermeable skins to prevent water loss, and highly efficient kidneys or equivalent organs that recycle water internally. Plant analogues might photosynthesize only at night when temperatures drop and humidity rises, closing all pores during the day to prevent water loss. Despite the harsh conditions, life could potentially thrive in sheltered microenvironments, shaded canyons, caves where humidity condenses, or underground where water from ancient aquifers remains accessible. Eyeball planets emerge around red dwarf stars when planets become tidally locked, always showing the same face to their star, with one hemisphere in permanent daylight and the other in eternal darkness. The day side receives constant intense heating, potentially creating a hot desert. The night side, receiving no sunlight, freezes solid. But at the terminator, the boundary between day and night, a ring of habitable conditions might exist where temperatures remain moderate. This ring might harbour a circular ocean, the eyeball, surrounded by ice on one side and desert on the other, creating a narrow band where life could flourish. Life on eyeball planets would be restricted to this habitable ring, adapted to conditions that never change. No day-night cycle, no seasons, just constant twilight with the star permanently fixed at the horizon. Organisms might spread around the entire circumference of the planet along this habitable band, but they couldn't expand toward either pole. Moving toward the substellar point would lead to lethal heat. Moving toward the antistellar point would lead to frozen darkness. The planet's climate would feature constant winds, as air heated on the day side rises and flows toward the cold night side, creating atmospheric circulation patterns completely unlike Earth's weather. Super-Earths, rocky planets more massive than Earth, but less massive than Neptune, might be the most common type of habitable planet in the galaxy, despite having no analogue in our solar system. These worlds, with masses ranging from about 2 to 10 times Earth's mass, would have stronger surface gravity than Earth. An organism on a super-Earth twice Earth's mass might weigh twice what it would on Earth, creating challenges for movement and structural support, but super-Earths have potential advantages for habitability. Their stronger gravity can hold thicker atmospheres more effectively, providing better greenhouse warming and allowing habitable zones to extend farther from their stars. They might have more active plate tectonics due to greater internal heat, helping regulate climate over geological time. Life on super-Earths would likely evolve shorter, stockier body plans to cope with high gravity. Trees might be shorter and thicker. Animals might have more legs or stronger, thicker legs to support their weight. Flight might be more difficult, requiring more powerful wings and muscles. But the thicker atmosphere might actually make flight easier by providing more air resistance, potentially allowing organisms to evolve gliding or flying capabilities using less energy than on Earth, despite the higher gravity. Mini-Neptunes, planets with substantial hydrogen-helium atmospheres surrounding rocky or icy cores, represent a planet type between rocky super-Earths and gas giants. These worlds might not be habitable at their cloud tops where temperatures and pressures are moderate, but atmospheres are thick hydrogen-helium mixtures. However, some mini-Neptunes might have layers within their atmospheres where temperature and pressure allow water vapor to condense into liquid water droplets, creating water clouds and potentially habitable conditions within the atmosphere itself. Aerial life in these water clouds, floating organisms that never touch solid ground because there is no solid ground accessible, might evolve. Such organisms would need to regulate their buoyancy, perhaps using gas-filled bladders similar to fish swim bladders. They might extract nutrients from atmospheric chemistry or from particles suspended in the atmosphere. Reproduction might involve releasing spores or offspring that drift through the atmosphere until they find suitable conditions to grow. The entire biosphere would be three-dimensional and airborne, with no connection to any surface. Hycean worlds, a term combining hydrogen and ocean, represent a recently proposed planet type that might be surprisingly common and habitable. These are large planets with hydrogen-rich atmospheres and liquid water oceans beneath them, potentially including some mini-Neptunes if conditions are right. The thick hydrogen atmospheres would create greenhouse warming that keeps water liquid even at large distances from the star. Life on Hycean worlds would live in the oceans beneath kilometers of hydrogen atmosphere, never exposed to space but potentially able to thrive in the dark, high-pressure water below. The discovery of biosignatures on Hycean worlds might be easier than on Earth-like planets because their larger sizes and extended atmospheres make spectroscopic analysis more favourable. If life produces gases that reach the hydrogen atmosphere, methane, dimethyl sulfide, or other organic compounds, these might be detectable even with current telescope technology. Hycean worlds thus represent prime targets for near-term biosignature searches. Carbon planets might form in regions of protoplanetary disks, where carbon is more abundant relative to oxygen than in our solar system. Instead of being dominated by silicate minerals like Earth, these worlds might have surfaces and interiors rich in graphite, diamond, silicon carbide, and other carbon compounds. The chemistry of such worlds would be radically different from Earth's. Oceans might consist of hydrocarbons, liquid methane, ethane, or more complex carbon compounds, rather than water. Life on carbon planets, if it evolved, would necessarily use chemistry adapted to carbon-rich, oxygen-poor conditions, potentially resembling the hydrocarbon-based biochemistry speculated for Titan. Lava worlds orbit so close to their stars that surface temperatures exceed the melting points of rock. These planets have surfaces of molten lava with atmospheres of vaporized rock, silicate gases that condense into mineral clouds and rain molten droplets. No life as we imagine it could survive on these surfaces, but some scientists speculate about exotic life existing in the upper atmosphere, where temperatures are lower, or about subsurface oceans trapped beneath the molten surface, where water remains liquid despite the hellish conditions above. Ice worlds covered by thick shells of water ice might be habitable not on their surfaces, which are frozen solid, but in subsurface oceans kept liquid by tidal heating from their parent planet's gravity. Jupiter's moon, Europa, and Saturn's moon, Enceladus, represent examples in our own solar system. Such worlds might be common around giant planets throughout the galaxy. The ice shell provides protection from radiation and impact, while the liquid ocean beneath could harbour extensive ecosystems based on chemical energy from hydrothermal vents rather than sunlight. These worlds would have dark biospheres, no photosynthesis, no dependence on their star, just chemosynthetic life, thriving in hidden seas. Rogue planets drifting through interstellar space with no star at all might still be habitable if they're massive enough to retain thick atmospheres that provide greenhouse warming through atmospheric pressure alone. A rogue Earth-mass planet with a very thick hydrogen atmosphere might maintain liquid water on its surface, despite receiving no starlight, heated only by residual internal radioactive decay and gravitational contraction. Life on such a world would exist in perpetual darkness, depending entirely on chemical energy and internal heat, completely independent of any star. A truly alien biosphere that could drift for billions of years through the void between stars. Binary planet systems where two similarly sized worlds orbit their common center of mass, like Pluto and Charon but potentially both habitable, might create unique conditions. Tidal forces between the planets would generate internal heating. The planets would raise tides on each other. If both have atmospheres, atmospheric circulation might be affected by the nearby companion. Life might evolve on both worlds simultaneously, potentially following different evolutionary paths, or life might spread from one to the other via meteorite impacts that eject material-carrying microorganisms between the two worlds. Trojan planets sharing the same orbit around a star, positioned at stable Lagrange, 0.60 degrees ahead of or behind each other, might exist in some systems. These planets would orbit at the same distance from their star, but would see each other as bright points in the sky, visible like particularly bright stars. If both are habitable, civilizations might arise on both, potentially detecting each other's presence long before achieving space travel, since the neighbouring world would be so prominent in their sky. The different types of habitable planets extend far beyond Earth analogues to encompass ocean worlds with global seas, desert planets with scarce water, tidally locked eyeball planets with habitable rings, massive super-Earths with strong gravity, aerial biospheres in thick atmospheres, subsurface oceans beneath ice shells, hydrocarbon-based chemistry on carbon planets, and rogue worlds wandering starless through the galaxy, each type presenting unique challenges and opportunities for life, each potentially harbouring biospheres as rich and complex as Earth's, despite being profoundly different in their physical conditions, demonstrating that the cosmos might contain not just one type of living world, but a vast diversity of habitable environments where chemistry, energy, and time have combined to create the extraordinary phenomenon we call life, scattered across countless worlds in forms we're only beginning to imagine. What alien oceans might contain? Earth's oceans are vast, salty bodies of liquid water covering more than 70% of the planet's surface, containing dissolved minerals, organic molecules, and a staggering diversity of life, from microscopic bacteria to the largest animals that have ever existed. But oceans on other worlds might be fundamentally different, not just in what organisms inhabit them, but in their very composition, what liquids fill them, what chemicals dissolve in those liquids, and what physical conditions prevail at their depths. Understanding what alien oceans might contain means considering not only water-based oceans with different chemistry than Earth's seas, but entirely different liquids that could serve as oceanic solvents on worlds with radically different temperatures, pressures, and geological histories. The most familiar alien oceans would be water-based oceans on other worlds. Several candidates exist in our own solar system. Europa, Jupiter's ice-covered moon, harbours a global ocean containing perhaps twice as much liquid water as all of Earth's oceans combined, kept liquid by tidal heating from Jupiter's gravity despite surface temperatures around -160 degrees Celsius. This ocean lies beneath an ice shell estimated to be 15 to 25 kilometers thick, shielding the water from the vacuum of space and from Jupiter's intense radiation belts. What Europa's ocean contains remains unknown, but scientific models and the limited data from spacecraft flybys provide clues. The ocean is certainly salty, likely containing dissolved salts leached from Europa's rocky seafloor over billions of years. Magnesium sulfate, sodium chloride, and other salts detected spectroscopically in Europa's ice shell probably came from the ocean below. The salinity might be similar to Earth's oceans, or it might be substantially higher, creating a briny sea where salt concentrations affect water's freezing point, density, and chemistry. High salinity would influence what kinds of life could potentially evolve, favouring organisms with mechanisms to cope with osmotic stress. The ocean would be dark. Absolutely no sunlight penetrates through kilometres of ice. Any life in Europa's ocean would depend on chemical energy rather than photosynthesis. The rocky seafloor might host hydrothermal vents similar to those on Earth's ocean floor, where hot, mineral-rich water spews from cracks in the rock, driven by volcanic heat from the moon's interior. These vents could provide energy and nutrients to support chemosynthetic bacteria that extract energy from chemicals in the vent fluids: hydrogen, methane, hydrogen sulfide, iron compounds. If such microbes exist, they might form the base of a food chain, supporting more complex organisms analogous to the tube worms, clams, and crustaceans that cluster around Earth's hydrothermal vents. Dissolved gases would be present in Europa's ocean: carbon dioxide from reactions between water and rock, hydrogen from water-rock reactions, and possibly from radiolysis, where radiation breaks apart water molecules near the ice-ocean boundary, methane from geological processes, or potentially from biological activity. The concentrations and ratios of these gases would reveal much about the ocean's chemistry and whether biological processes might be occurring. Organic molecules, carbon-based compounds, almost certainly exist in Europa's ocean. Comets and meteorites containing organic compounds have bombarded Europa throughout its history. Chemical reactions between water and rock produce simple organic molecules. If life exists, it would produce far more complex organic molecules: amino acids, lipids, sugars, proteins. Detecting complex organic molecules in samples from Europa's ocean would be strong evidence for biology, though distinguishing biological from non-biological organic chemistry would require careful analysis. Enceladus, Saturn's small moon, provides an even more accessible alien ocean because it actively vents ocean water into space through cracks in its south polar ice shell. The Cassini spacecraft flew through these plumes, analysing their composition directly. The plumes contain water vapour, ice grains, carbon dioxide, methane, ammonia, molecular hydrogen, and complex organic molecules, including some with chains of carbon atoms, ingredients that on Earth would suggest habitability. The presence of molecular hydrogen is particularly intriguing because it suggests water-rock reactions at high temperatures, consistent with hydrothermal vents on Enceladus's seafloor. The organic molecules, while not proof of life, show that organic chemistry is occurring in Enceladus's ocean. Titan, Saturn's largest moon, presents an entirely different type of ocean. Not water, but liquid hydrocarbons. Titan's surface temperature hovers around -180 degrees Celsius, far too cold for liquid water, which is frozen as hard as rock. But at these temperatures, methane and ethane exist as liquids. Titan has lakes and seas of liquid hydrocarbons near its poles, bodies of liquid methane and ethane with dissolved propane, butane, nitrogen, and traces of more complex organic molecules. These hydrocarbon seas are hundreds of meters deep in some places, creating environments completely unlike anything on Earth. What Titan's hydrocarbon oceans might contain depends on what chemistry can occur in liquid methane at cryogenic temperatures. Organic chemistry certainly happens. Titan's atmosphere produces complex organic molecules through photochemistry, and these molecules rain down onto the surface, accumulating in the lakes and seas. Nitrogen compounds, cyclic molecules, long-chain hydrocarbons, and possibly even more complex molecules might dissolve in the methane. Whether life could exist in liquid methane remains highly speculative, but if it does, it would use completely different biochemistry than Earth life, perhaps with cell membranes made from molecules that are insoluble in hydrocarbons rather than the water-soluble membranes Earth organisms use. Titan also likely has a subsurface water ocean beneath its icy crust, similar to Europa and Enceladus. This buried ocean would be separate from the surface hydrocarbon seas, creating the possibility that Titan might host two completely different types of chemistry: water-based chemistry in the deep subsurface ocean and hydrocarbon-based chemistry in the surface seas. Whether these two environments could both support life, and whether life in one could be related to life in the other, represents one of the most intriguing questions about this remarkable moon. Ammonia oceans represent another possibility for alien seas. Ammonia remains liquid at temperatures between -77 and -33 degrees Celsius at Earth atmospheric pressure, colder than water but warmer than methane. A planet or moon with temperatures in this range might have oceans of liquid ammonia or ammonia-water mixtures. Pure ammonia is a less effective solvent than water for many compounds, but it can dissolve different substances than water, creating entirely different ocean chemistry. An ammonia ocean would be less dense than water ice, so ammonia ice would sink rather than float, potentially affecting planetary heat transport and ocean circulation. The ocean's pH would be highly alkaline. Ammonia is a base, creating chemistry very different from Earth's near-neutral oceans. Organisms adapted to ammonia oceans would need biochemistry that functions at low temperatures and high pH, potentially using ammonia molecules in ways analogous to how Earth life uses water. Sulfuric acid oceans sound implausible, yet Venus's clouds contain concentrated sulfuric acid droplets, and some scientists have speculated about life existing in these droplets. While Venus's surface is hellishly hot, the cloud layers at altitudes of 50 to 60 kilometers above the surface have temperatures around room temperature, quite comfortable by terrestrial standards. If life could exist as airborne organisms living in cloud droplets, those droplets would be concentrated sulfuric acid, requiring biochemistry completely unlike anything on Earth. Certain Earth microbes can tolerate extremely acidic conditions, proving that acid-resistant biochemistry is possible. But whether life could actually live in sulfuric acid remains unknown and highly controversial. Silicate oceans, molten rock, might exist on lava worlds orbiting extremely close to their stars. At temperatures exceeding 2000 degrees Celsius, rock melts into liquid magma that flows like water. While most scientists consider molten rock too hot and destructive for any conceivable biochemistry, some speculative theories propose exotic life forms based on completely different chemistry that might exist in magma, perhaps using silicate molecules or metal compounds as structural materials instead of carbon-based organic molecules. Such life would be so alien that we might not recognize it as life, even if we observed it directly. Supercritical oceans exist under conditions where temperature and pressure are high enough that the distinction between liquid and gas breaks down. Supercritical water, existing at temperatures above 374 degrees Celsius and pressures above 220 atmospheres, has properties intermediate between liquid and gas. Deep beneath the surfaces of massive ocean worlds, pressures might be high enough to create supercritical water oceans. The chemistry in supercritical water differs dramatically from normal water chemistry, with different solubilities, reaction rates, and molecular interactions. Whether life could adapt to supercritical conditions remains unknown, but the possibility can't be ruled out for extremely exotic organisms. The ocean floor composition profoundly affects ocean chemistry. Earth's ocean floors are basaltic rock, and water-rock interactions continuously cycle elements between the ocean and the crust. Alien ocean floors might be different, perhaps pure ice if the ocean is deep enough that high-pressure ice forms at the bottom, or perhaps carbonate rocks, serpentinite, or other minerals depending on the planet's composition. These different minerals would leach different elements into the ocean, creating different dissolved chemistry. Hydrothermal vents on alien seafloors might vent fluids with very different composition than Earth's vents. On Europa or Enceladus, where the rocky interiors might be rich in different minerals than Earth's mantle, vent fluids might contain unusual concentrations of metals, sulfur compounds, or other chemicals. These different chemistries would favor different types of chemosynthetic organisms if life exists, potentially creating ecosystems with no analogue on Earth. Dissolved oxygen would be rare or absent in most alien oceans unless photosynthetic life has evolved and produced oxygen for billions of years as on Earth. Most alien oceans would be anoxic, without dissolved oxygen, more similar to Earth's oceans before the Great Oxidation Event 2.5 billion years ago. Anoxic oceans contain different dissolved metals and have different chemistry than oxygenated oceans. Iron remains dissolved in anoxic water instead of precipitating as rust. Sulfur chemistry dominates, rather than oxygen chemistry. Life in anoxic alien oceans would use anaerobic metabolism, extracting energy from reactions that don't involve oxygen. Temperature gradients in alien oceans depend on heat sources. Earth's oceans are heated from above by sunlight and from below by geothermal heat, creating complex circulation patterns. Europa's ocean, heated only from below by tidal heating and with a cold ice ceiling above, might have upside-down circulation compared to Earth. Warm water rising from the seafloor toward the ice ceiling where it cools and sinks back down. These circulation patterns would affect nutrient distribution, temperature zones, and where life might be most abundant. Pressure increases with depth in any ocean, but the rate depends on the liquid's density and the world's gravity. Europa's ocean might reach pressures exceeding 10,000 atmospheres at the seafloor, much higher than Earth's deepest ocean trenches, due to the ocean's great depth. Organisms adapted to such extreme pressure would have specialized biochemistry that functions under conditions where molecules are compressed and reaction rates are altered by pressure's effects on molecular structure. Seasonal variations might affect some alien oceans. A planet with significant axial tilt would experience seasonal changes in star heating that could affect surface ocean temperatures, causing seasonal mixing, ice formation and melting, and biological cycles tied to seasons. Tidally locked planets would have no seasonal variations, but might have temperature zones related to distance from the substellar point, the location where the star is directly overhead, creating warm equatorial regions and cold polar regions, with different ocean chemistry in each zone. Ice-covered oceans might have ecosystems concentrated near the ice-water boundary, where any photosynthesis using radiation penetrating through cracks in the ice could occur, or where chemical gradients between the ice and deep ocean creates energy harvesting opportunities. Life might cluster in cracks and crevices in the ice ceiling, or in regions where the ice is thinnest and most likely to crack or melt. What alien oceans might contain ranges from the familiar salty water with dissolved minerals and potentially abundant life, to the exotic, liquid methane seas with dissolved organic compounds, ammonia oceans at cryogenic temperatures, supercritical fluids blurring the line between liquid and gas, even molten silicate magmas on scorching hot worlds. Each ocean's composition reflects its world's temperature, pressure, geology, and history, creating environments where chemistry operates under different rules, where life, if it exists, would be adapted to conditions we can barely imagine, where exploration by future spacecraft might reveal ecosystems as diverse and wondrous as Earth's oceans, or so alien that we struggle to recognize biology when we see it, expanding the inventory of habitable environments to include not just Earth-like water oceans, but any stable liquid where dissolved chemicals, energy sources, and sufficient time might allow chemistry to evolve into biology beneath the waves of alien seas scattered across the solar system and beyond. What alien civilizations might actually look like? When most people imagine alien civilizations, they picture humanoid beings with large heads, sleek bodies, and advanced technology that allows them to cross the vast distances between stars. Science fiction has given us countless variations: green-skinned Martians, insectoid hive minds, crystalline energy beings, peaceful explorers, and hostile invaders alike. But what would alien civilizations actually look like if we base our expectations on biology, physics, chemistry, and evolutionary principles rather than imagination alone? The answer reveals possibilities both familiar and utterly strange, shaped by the same fundamental laws that govern life on Earth, but expressed through the infinite variations that different worlds and evolutionary histories would create. The foundation of any alien civilization begins with evolution. On Earth, every organism exists because its ancestors survived and reproduced more successfully than competitors. Natural selection shaped everything from bacterial flagella to human brains, optimizing organisms for their specific environments and challenges. The same process would operate on any world where life exists. Alien organisms would be shaped by their planet's gravity, atmosphere, temperature, available nutrients, predators, and countless other factors operating over millions or billions of years. Evolution is relentless, creative, and opportunistic, finding solutions to survival challenges through whatever mechanisms work. Gravity would profoundly influence alien body structures. On a high-gravity planet, perhaps 1.5 times Earth's gravity, organisms would need stronger skeletal structures to support their weight. Animals might evolve shorter, stockier bodies with thicker bones and more powerful muscles. Tall, slender forms would be disadvantageous because they would require too much structural support and energy to maintain. Intelligent beings on such a world might stand only 3 or 4 feet tall despite being as massive as humans, with powerful legs and low centers of gravity to move efficiently under the stronger gravitational pull. On a low-gravity planet, the opposite constraints would apply. With less gravitational force to overcome, organisms could grow taller and more delicate. Bones could be lighter and more slender. Flying might be easier, allowing evolution to produce larger flying organisms than Earth's giant pterosaurs. Intelligent beings might stand 8 or 10 feet tall with elongated limbs, moving with a grace that would seem almost balletic to Earth-based observers. Their skeletal structure might resemble bird bones, hollow and reinforced with internal struts rather than solid like mammalian bones. The atmospheric composition would shape how aliens breathe and what biochemistry they use. On Earth, most complex life uses oxygen for metabolism because burning fuel with oxygen releases large amounts of energy efficiently. But oxygen was not always abundant. Early Earth had an atmosphere dominated by nitrogen, carbon dioxide, methane, and other gases. The oxygen we breathe today came from photosynthetic bacteria that gradually transformed the atmosphere over billions of years in what's called the Great Oxidation Event. An alien planet might never undergo such a transformation, leaving its atmosphere oxygen poor. Life there might use different metabolic pathways, perhaps based on sulfur compounds, hydrogen, or methane. The type of star a planet orbits would influence alien vision and perhaps their entire sensory experience of reality. Our sun emits most strongly in visible light wavelengths, the colours we can see. And Earth's organisms evolved eyes sensitive to these wavelengths because that's where the most light was available. But a planet orbiting a red dwarf star would receive most of its light in infrared wavelengths. Organisms evolving there might develop eyes sensitive to infrared rather than visible light. To them, what we call visible light might be invisible ultraviolet, and their daylight would be our infrared. An alien from such a world would perceive colours and see objects in ways completely foreign to human experience. Conversely, a planet orbiting a hotter, bluer star would receive more ultraviolet light. Evolution might produce eyes sensitive to ultraviolet wavelengths, allowing these aliens to see patterns and colours invisible to humans. Many Earth organisms, including bees and some birds, can already see into the ultraviolet range, perceiving patterns on flowers and plumage that humans cannot detect without special cameras. An alien species with full ultraviolet vision would experience a visual world enriched with information and beauty we cannot access. Communication methods would evolve based on environmental constraints and available sensory channels. On Earth, humans primarily communicate through sound, speaking and hearing, supplemented by visual cues like facial expressions and gestures. But sound travels poorly, in thin atmospheres, and not at all in vacuum. An alien species on a world with a thin atmosphere might rely more heavily on visual communication, colour changes, bioluminescent patterns, or elaborate gestural languages. Octopuses on Earth already use colour-changing skin cells, called chromatophores, to communicate, creating flowing patterns across their bodies. An intelligent species with similar abilities might communicate through rapidly shifting colour displays, conveying complex ideas through patterns that flow across their skin in what would appear to us as living art. Some aliens might communicate through vibrations transmitted through the ground or through their planet's oceans. Whales and elephants on Earth use low-frequency sounds that travel great distances. Elephant calls can travel several miles through the ground. An intelligent species might evolve specialized organs for creating and detecting vibrations, communicating through seismic signals that travel through rock or sediment. Their language would be invisible and inaudible to humans without special equipment to detect the vibrations. Chemical communication, already used extensively by Earth's insects through pheromones, might become the primary communication method for some species. Aliens might communicate through releasing complex mixtures of chemicals that other members of their species detect through sensitive chemoreceptors. Their language would consist of scents and tastes, with grammar and syntax encoded in the ratios and combinations of different molecules. To humans, their most profound poetry and scientific papers would be nothing more than smells. Body structure would reflect evolutionary history and environmental pressures. The bilateral symmetry seen in most Earth animals, a left side mirroring a right side, emerged early in evolution and became locked in. But aliens might evolve radial symmetry, like starfish, with body parts arranged around a central axis. An intelligent being with radial symmetry might have arms, eyes, and sensory organs distributed evenly around their body, giving them a 360-degree field of awareness with no natural front or back. Their psychology and culture might be profoundly affected by experiencing the world without a preferred direction of travel or attention. The number of limbs is not fixed by any physical law. Earth's vertebrates settled on 4 limbs relatively early in evolutionary history, but arthropods, insects, spiders, crustaceans have 6, 8, or even dozens of legs. An alien species might evolve with 3 limbs arranged in a triangle, giving them stable tripod support at all times. They might have 6 limbs, 4 for walking and 2 manipulator arms. Or they might have dozens of tentacles like an octopus, each capable of independent complex movement and manipulation. Their tool use and technology would develop along entirely different lines than human technology, shaped by their different manipulative abilities. Intelligence itself might manifest in forms unlike human intelligence. Human intelligence is highly centralized. Most of our cognitive processing occurs in our brain, a single organ in our head. But octopuses, among Earth's most intelligent invertebrates, have a distributed nervous system with neurons throughout their arms that can make independent decisions. An alien species might have multiple brain centers distributed throughout their body, or they might have a collective intelligence where individual organisms are relatively simple, but groups display emergent intelligence through their interactions, similar to how ant colonies solve complex problems that individual ants cannot. Social structure would influence civilization development. Humans are intensely social primates who naturally form groups, cooperate, compete, and create complex hierarchies. An intelligent species that evolved from solitary predators might have very different social instincts, perhaps coming together only to mate and raise young, then separating again. Their civilization would be built by individuals who value isolation and independence over community and cooperation. Or aliens might be eusocial, like bees or ants, with specialized castes, workers, soldiers, reproducers, genetically programmed for different roles. Their civilization might function as a superorganism where individual identity barely exists. Lifespan would profoundly affect culture and technology development. If an alien species naturally lives for thousands of years, they might approach problems with a patience humans cannot fathom, willing to spend centuries on single projects. Their sense of urgency and change would operate on timescales that would frustrate any human trying to interact with them. Conversely, a species with lifespans of only a few years might compress their entire cultural and technological development into periods that humans would find incomprehensibly rapid. Environmental factors would shape not just biology, but psychology and culture. A species that evolved in oceans might think about space and boundaries very differently than land-dwelling humans. Without solid ground beneath them, without permanent structures that last for generations, their concepts of property, territory, and permanence might be fluid in ways humans struggle to understand. A species that evolved in dense forests with limited sightlines might have very different concepts of distance and perspective than humans who evolved in open savannas, where seeing for miles was possible and valuable. Technology would develop based on available resources and environmental challenges. A civilization on a water world with no dry land would never discover fire, fundamentally altering their technological development pathway. Without fire, they couldn't easily work metals, make pottery, or develop steam power. Their technology might focus on biological engineering, breeding organisms to serve specific functions, or on working with materials that don't require heat processing. They might develop advanced understanding of hydrodynamics, pressure, and acoustic phenomena, while lacking technologies that humans developed early. A civilization on a planet with extreme temperature swings might prioritize insulation and environmental control. A species on a tidally locked planet, with one side in permanent daylight and the other in eternal darkness, might build their civilization in the twilight zone between extremes. Or they might develop two separate cultures, adapted to the radically different environments. Their technology would need to handle these extremes, perhaps leading to advanced materials science long before other fields developed. Reproduction methods would influence family structures and social organization. If aliens reproduce through spawning like fish, releasing eggs and sperm into water where fertilization occurs externally, they might have no concept of nuclear family or parental bonds. Eggs might be raised communally or even left to develop independently. If reproduction requires 3 or more sexes simultaneously, their social structures and mating rituals would be incomprehensibly complex to humans. If they reproduce through budding or fission, creating genetic copies of themselves, their concepts of individuality and identity might be fundamentally different from species that reproduce sexually and value genetic diversity. Sensory experiences beyond human comprehension might exist. Some Earth organisms detect magnetic fields, electric fields, pressure changes, or polarized light, senses humans lack entirely. An alien species might perceive reality through senses we don't possess and cannot easily imagine. They might see the world through echolocation like bats, building a sonic map of their environment. They might sense electrical fields like sharks detecting the bioelectric signatures of other organisms. They might perceive time differently, with reaction times much faster or slower than humans, making their subjective experience of duration incompatible with ours. The Fermi paradox asks why, if alien civilizations are likely to exist, we haven't detected them yet. One possible answer is that we're looking for the wrong things. We search for radio signals because that's how we communicate, and we look for visible structures, like cities, because that's how we build. But an alien civilization might never develop radio technology, using entirely different communication methods. They might build in ways that leave no visible trace from space. They might exist on entirely different timescales, civilizations that rise and fall in centuries, while humans are still learning to farm, or civilizations that operate so slowly that their entire recorded history spans less time than a human lifetime. If contact ever occurs between human and alien civilizations, the challenges would be immense. Even if both species are trying to communicate, fundamental differences in sensory experience, cognition, timescales, and conceptual frameworks might make mutual understanding nearly impossible. Imagine trying to explain color to someone born blind, or music to someone born deaf, or love to a species that doesn't experience emotions. Now multiply those challenges by every aspect of existence: time, space, causation, identity, purpose. Communication might require generations of effort and specialized translation technologies we haven't yet imagined. What alien civilizations might actually look like encompasses possibilities ranging from vaguely familiar, carbon-based organisms breathing oxygen on Earth-like worlds shaped by convergent evolution into forms somewhat similar to Earth's creatures, to utterly incomprehensible beings whose very existence challenges our definitions of life, intelligence, and civilization. They might be silicon-based entities living in molten rock at temperatures that would vaporize Earth's organisms. They might be electromagnetic patterns in planetary magnetic fields, or chemical reaction networks in liquid methane seas, or quantum coherence patterns in neutron star crusts. The universe is vast and ancient, and if intelligence has emerged elsewhere, it has had billions of years and countless different environments in which to develop into forms limited only by physics, chemistry, and the creative power of evolution operating across deep time on worlds we've never seen.